The James Webb Space Telescope has done it again. And this time, there really is no going back from what it found. One of the oldest galaxies ever seen by human eyes. A galaxy so ancient that its light started traveling toward us just a few 100 million years after the Big Bang itself. When scientists finally processed what they were looking at, one of them said it was like finding a lost city in an archaeological dig, something nobody expected to exist. But here is what makes this discovery so troubling for everything we thought we knew. This galaxy should not look the way it does. It is too bright, too big, too mature, and its very existence is forcing scientists to question whether our understanding of how the universe works is actually correct. So what exactly did the James Webb Space Telescope find out there in the darkness of space? And why are some researchers saying that this discovery might change everything? To understand why this ancient galaxy matters so much, we need to first understand how telescopes actually see back in time. And yes, they really do see back in time. This is not science fiction. This is just how the universe works. Light travels fast, but it does not travel instantly. Light moves through space at about 186,000 miles every single second. That sounds impossibly quick, and for anything happening here on Earth, it basically is instant. When you flip on a light switch in your kitchen, the light reaches your eyes so fast that you cannot even notice the delay. But the universe is unimaginably vast. And out there, across the cosmic distances between stars and galaxies, that travel time starts to add up in a big way. Think about our own sun. It sits about 93 million miles away from Earth. Light from the sun takes about 8 minutes to reach us. So when you look up at the sun, you are not seeing it as it is right now. You are seeing it as it was 8 minutes ago. If the sun suddenly vanished, we would not know about it for 8 whole minutes. We would still see it shining in the sky until that last bit of light finished its journey to our eyes. Now stretch that concept further. The nearest star to our solar system besides the sun is called Proxima Centauri. It sits about 4 light years away. A light year is the distance light travels in 1 whole year, which works out to roughly 6 trillion miles. So when astronomers point their telescopes at Proxima Centauri, they are seeing light that left that star 4 years ago. They are looking at the past, go even further out, and the time delays become truly mind-bending. The Andromeda Galaxy, which is our nearest major galactic neighbor, sits about 2.5 million light-years away. When you look at Andromeda through a telescope, you are seeing light that began its journey toward Earth 2.5 million years ago, back when early human ancestors were just starting to walk upright on the African plains. That light has been traveling through empty space for longer than modern humans have even existed as a species. This is the beautiful trick that lets astronomers study the history of the universe. The further out they look, the further back in time they see, and the James Webb Space Telescope was built specifically to look further out than any telescope before it, to peer so deep into the cosmos that it can see the universe as it existed in its infancy. Just a few 100 million years after the Big Bang that started everything. The telescope orbits the sun about 1 million miles away from Earth, at a special point in space called the second Lagrange point. Out there, it sits in perpetual shadow, protected from the heat and light of the sun, Earth, and moon. This matters because the Webb telescope sees the universe in infrared light, which is basically heat radiation. If the telescope itself was warm, its own heat would blind its incredibly sensitive instruments, so it needs to stay cold. Incredibly cold. The instruments on board are chilled down to temperatures around minus 400 degrees Fahrenheit. Colder than any natural environment on Earth, colder even than the surface of Pluto. The telescope carries a massive mirror to collect as much light as possible from distant objects. This mirror stretches over 21 feet across and is made up of 18 hexagonal segments coated in a microscopically thin layer of pure gold. The gold is there because it reflects infrared light exceptionally well. Each mirror segment weighs about 46 pounds and is made from a special metal called beryllium, which stays stable even at cryogenic temperatures. The segments had to be folded up like origami to fit inside the rocket that launched the telescope into space. Then, after launch, mechanical systems carefully unfolded everything and aligned the segments with incredible precision. Each segment had to be positioned within 1/10,000th the thickness of a human hair. Engineers had to invent entirely new technologies to make that possible. Why go through all this trouble to see infrared light from ancient galaxies? The answer has to do with how light behaves as it travels across an expanding universe, and why infrared observations are so crucial for studying the early cosmos. When physicists say the universe is expanding, they do not mean that galaxies are flying through space away from each other like shrapnel from an explosion. Instead, space itself is stretching. Imagine drawing dots on a balloon and then inflating the balloon. The dots do not move across the surface of the balloon, but the distances between them increase as the balloon expands. That is roughly what is happening to the universe. Galaxies are not moving through space so much as space is growing between them. This cosmic expansion has profound effects on light traveling through the universe. Consider a beam of light leaving a distant galaxy. As that light travels toward us, the universe keeps expanding. The wavelength of the light gets stretched along with the stretching space. By the time the light reaches Earth, its wavelength is longer than it was when it started its journey. For light from very distant objects, this stretching can be extreme. Visible light has wavelengths measured in hundreds of nanometers, with blue light at the short end and red light at the long end. When light gets stretched to longer wavelengths, it shifts toward the red end of the visible spectrum. That is why scientists call this effect redshift. Push the stretching far enough and the light shifts entirely out of the visible range and into the infrared portion of the spectrum. Infrared light has wavelengths thousands of nanometers long, invisible to human eyes but detectable with specialized instruments. The most distant objects in the universe have experienced the most stretching because their light has been traveling the longest. Galaxies from the first few 100 million years of cosmic history are so extremely redshifted that their ultraviolet and visible light has been stretched all the way into the mid-infrared range. No optical telescope, no matter how powerful, can see these objects. Their light simply is not in the right part of the spectrum. Only an infrared telescope optimized for the specific wavelengths where this stretched ancient light appears can detect them. This is exactly why the James Webb Space Telescope was designed the way it was. Its instruments are tuned to infrared wavelengths from about 1 micrometer to nearly 30 micrometers, spanning the near and mid-infrared parts of the spectrum. This is the range where light from the earliest galaxies appears after its epic journey across 13+ billion years of cosmic expansion. The telescope's gold-coated mirrors reflect infrared light far better than silver or aluminum coatings would. Its cryogenic cooling keeps the instruments cold enough that their own thermal radiation does not interfere with the faint signals from distant galaxies. Every design choice was made with this single goal in mind: to see the infrared glow of the most ancient light in the universe. When the universe was young, those early galaxies gave off normal, visible light, just like the stars we see in our night sky today. But as that light traveled across billions of years, something strange happened to it. The universe itself was expanding the whole time, stretching the fabric of space in every direction. And as space stretched, the light traveling through it got stretched too. Its wavelengths got longer, shifting the light from visible colors into infrared wavelengths that our eyes cannot see. Scientists call this effect redshift, because visible light that gets stretched tends to shift toward the red end of the spectrum before eventually passing entirely into infrared. The most distant objects in the universe have experienced the most stretching. Their light has traveled the longest and passed through the most cosmic expansion. So by the time that light reaches us, it has been shifted so far into the infrared that only a telescope like the James Webb can see it. The Hubble Space Telescope, which came before Webb, could see some of this stretched light, but not the most extremely redshifted objects. Hubble peered back to about 400 million years after the Big Bang. But Webb can see even further, potentially all the way back to when the very first stars and galaxies were just beginning to form. And that brings us to the discovery that is shaking up the scientific world. A galaxy so distant that its light has been traveling toward us for over 13 billion years. A galaxy that formed when the universe was barely 2% of its current age. A galaxy that scientists are calling one of the most significant extragalactic discoveries ever made with the James Webb Space Telescope. The galaxy carries the official designation JADES GSZ 14-0. Scientists discovered it as part of a major observing program called JADES, which stands for the JWST Advanced Deep Extragalactic Survey. The JADES team pointed the Webb telescope at a small patch of sky for extended periods of time, building up incredibly deep images that reveal the faintest and most distant objects visible from Earth. It was in these images that the ancient galaxy first appeared. At first, the researchers were not sure what they were looking at. The object was surprisingly bright for something so far away. It also sat very close to another galaxy in the images, making the two appear almost connected. These unusual properties made the team cautious. Perhaps it was not actually as distant as the initial data suggested. Perhaps there was some confusion caused by the nearby galaxy. The scientists needed more observations to be certain, so they pointed the Webb telescope back at the mysterious object in late 2023. New imaging data from the telescope's near-infrared camera supported the hypothesis that this really was an incredibly distant galaxy. But the team still wanted definitive proof. They needed to obtain what astronomers call a spectrum, which is essentially a detailed fingerprint of light that reveals exactly what an object is made of and how far away it sits. In January 2024, the telescope's near-infrared spectrograph stared at the galaxy for almost 10 hours straight. When the data came back and the spectrum was processed, the results were unmistakable. The galaxy sits at what astronomers call a redshift of 14.32. Redshift is how astronomers measure cosmic distances, with higher numbers indicating greater distances and earlier cosmic times. A redshift of 14.32 means the light from this galaxy started traveling toward us when the universe was only about 290 million years old. Today, the universe is approximately 13.8 billion years old. So we are seeing this galaxy as it existed over 13 billion years ago. And at the time of its discovery, no other galaxy had ever been confirmed at such an extreme distance. The previous record holder for most distant galaxy was another object discovered by the Webb telescope with a redshift of just over 13. That galaxy existed about 330 million years after the Big Bang. The newly discovered galaxy pushed that record back by another 40 million years, which might not sound like much in a universe billions of years old. But in the rapidly evolving conditions of the early cosmos, 40 million years represented an enormous leap backward toward the very beginning of everything. And here is where the real mystery begins. When scientists look closely at the data from this ancient galaxy, they found that it does not behave the way early galaxies are supposed to behave. According to our best models of how the universe evolved, galaxies should have taken a long time to form after the Big Bang. The theoretical framework predicts a slow, gradual process of cosmic construction. In the moments after the Big Bang, the universe was unimaginably hot and dense. All of space was filled with a seething plasma of fundamental particles, too energetic to combine into atoms. As the universe expanded and cooled over the next few 100,000 years, conditions eventually became mild enough for protons and electrons to join together into neutral hydrogen atoms. This was a watershed moment. Before this, light could not travel far without being scattered by the charged particles that filled space. After this recombination, as physicists call it, light could travel freely for the first time. The universe became transparent, but transparent did not mean interesting. For hundreds of millions of years after recombination, the cosmos contained almost nothing but clouds of neutral hydrogen and helium gas, slowly cooling and drifting through expanding space. There were no stars, there were no galaxies, there was no light except for the gradually fading afterglow of the Big Bang itself. Astronomers call this era the cosmic dark ages because if you could somehow visit, you would see nothing but blackness in every direction. Eventually, gravity began to pull the gas together. The universe was not perfectly uniform. Tiny variations in density had been imprinted during the earliest moments after the Big Bang, and these variations served as seeds for future structure. Regions that were ever so slightly denser than average exerted slightly stronger gravitational pull on their surroundings. Over millions of years, this gentle tugging drew more and more gas into the overdense regions. The first dark matter halos formed, invisible scaffolds of exotic matter that concentrated even faster than the ordinary gas. Once enough gas had accumulated in the densest regions, something remarkable happened. Deep in the hearts of these gas clouds, where temperatures and densities had risen high enough, nuclear fusion ignited. The first stars were born. These primordial stars were strange by modern standards. Formed from oro, pure hydrogen and helium with no heavier elements, they burned hotter and brighter than any stars that exist today. Many were dozens or even hundreds of times more massive than our sun. They lived fast and died young, consuming their nuclear fuel in just a few million years before exploding in cataclysmic supernovas. These first supernovas scattered the first heavy elements into space. Carbon, oxygen, nitrogen, iron, and dozens of other elements that had never existed before were forged in stellar furnaces and dispersed by stellar explosions. This enriched gas then became available for the next generation of stars, which incorporated small amounts of these heavy elements into their composition. The cycle of stellar birth, death, and enrichment began, and it continues to this day. The first galaxies grew as more stars formed and more dark matter halos merged. Together, small protogalaxies combined into larger structures. Gas flowed in along filaments of dark matter, fueling new episodes of star formation. Black holes formed in the centers of galaxies and began to grow. Over hundreds of millions of years, the empty darkness of the cosmic dawn gradually filled with the light of emerging galaxies. All of this takes time. That is the key point. The standard theoretical framework predicts that building a galaxy with billions of solar masses of stars should require at least several hundred million years, probably closer to a billion. The first dark matter halos need time to form and merge. The gas needs time to cool and collapse. Stars need time to form, evolve, and die, scattering their enriched material for the next generation. Each step in the process has its own timescale, and these timescales add up. The very first stars needed to ignite. Those stars needed to burn through their fuel and explode, scattering heavier elements into space. New stars then needed to form from that enriched gas, creating the next generation. And gradually, over hundreds of millions of years, enough stars needed to cluster together under the pull of gravity to form recognizable galaxies. But this galaxy appears to have skipped ahead somehow. It is not a small, dim, primitive collection of early stars. It is bright, very bright. The light from this galaxy is too intense to come from a growing black hole at its center. Instead, the brightness comes from stars. Lots and lots of stars. The galaxy contains hundreds of millions of times the mass of our sun in stellar material, packed into a region over 1,600 light-years across. That is an enormous amount of star formation happening in the first 300 million years of cosmic history. The universe barely had time to form stars at all in that window, let alone create a galaxy this massive and luminous. Recent follow-up observations made the situation even more puzzling. When scientists examined the chemical composition of the galaxy using the Webb Telescope's mid-infrared instrument, they found something unexpected: oxygen. Substantial amounts of oxygen present in the gas and dust of this early galaxy. Now you might wonder why oxygen is surprising. Oxygen is one of the most common elements in the universe today. You are breathing it right now, rocks contain it, water is made of it. But oxygen did not exist at the beginning of the universe. The Big Bang only produced hydrogen, helium, and tiny traces of lithium. Everything else, including oxygen, carbon, nitrogen, and all the other elements that make up planets and living things, had to be forged inside stars and released into space when those stars died. For oxygen to exist in a galaxy only 300 million years after the Big Bang, that galaxy must have already gone through at least one complete cycle of stellar birth and death. The first generation of stars had to form, burn through their fuel, and explode as supernovas. Those explosions had to scatter oxygen atoms into the surrounding gas. Then new stars had to form from that enriched gas. The fact that this ancient galaxy already contains significant oxygen means star formation began even earlier than scientists previously thought. The timeline keeps getting pushed back. The universe was apparently building complex chemistry faster than our models predicted. And there is another strange finding related to this galaxy. Scientists detected unusual amounts of nitrogen in its spectrum. Nitrogen is an element that typically takes even longer to build up than oxygen. It requires multiple generations of stars to accumulate in significant quantities. Yet here it is, already present in one of the earliest galaxies ever observed. The theoretical models that predict how elements form in the early universe did not anticipate this much nitrogen this early. Something about our understanding of early stellar evolution appears to be incomplete. The discovery has profound implications for how many bright galaxies existed in the early universe. The team discovered this galaxy in a relatively small patch of sky. If objects like this are scattered throughout the cosmos at similar densities, then there must be far more of them out there than anyone expected. The early universe might have been teeming with large, bright, chemically complex galaxies rather than the sparse scattering of primitive protogalaxies that older models predicted. This has implications for everything from dark matter theory to our understanding of how black holes formed and grew. Speaking of dark matter, this is one of the great mysteries that Webb is helping scientists investigate. Dark matter is a hypothetical form of matter that does not interact with light in any way we can detect. It does not glow, it does not reflect, it does not absorb. The only way scientists know dark matter exists at all is through its gravitational effects on visible matter. The evidence for dark matter comes from multiple independent lines of observation spanning decades of astronomical research. The most famous evidence involves the rotation of galaxies. When astronomers measure how fast stars orbit around the centers of spiral galaxies, they find something deeply puzzling. Stars at the outer edges of galaxies are moving faster than they should be based on the gravitational pull of all the visible matter. If galaxies contained only the stars, gas, and dust that telescopes can see, the outer stars would be moving so fast that they should fly off into intergalactic space. But they do not. Something invisible is providing extra gravitational pull, keeping those fast-moving stars bound to their galaxies. Galaxy clusters provide even stronger evidence for dark matter. Clusters are enormous collections of hundreds or thousands of galaxies bound together by mutual gravitational attraction. When astronomers add up all the visible matter in a typical cluster, including the galaxies themselves plus the hot gas that fills the vast spaces between them, they find that it accounts for only a small fraction of the gravitational mass needed to hold the cluster together. Without some additional invisible mass, the galaxies in the cluster would fly apart. The clusters themselves would dissolve into the cosmic void. Yet the clusters persist, held together by the gravity of matter we cannot see. Gravitational lensing offers yet another line of evidence. When light from a distant background object passes through or near a massive foreground structure like a galaxy cluster, gravity bends the light and distorts the image. The amount of bending depends directly on how much mass the foreground structure contains. When astronomers measure the lensing caused by galaxy clusters and compare it to the visible matter present, they consistently find more bending than the visible matter alone can explain. The additional bending reveals the presence of invisible mass distributed throughout and around the cluster. Perhaps the most compelling evidence comes from the cosmic microwave background itself. This ancient radiation carries tiny temperature variations across the sky, slightly hotter in some directions and slightly cooler in others. The precise pattern of these variations encodes detailed information about the composition and history of the early universe. When cosmologists analyze this pattern with sophisticated statistical techniques, they can determine with remarkable precision how much ordinary matter and how much dark matter the universe contains. The answer is consistent across multiple independent measurements. Dark matter outweighs ordinary visible matter by about 5 to 1 throughout the cosmos. Despite all this evidence, scientists still do not know what dark matter actually is. It cannot be made of atoms or any of the familiar particles that constitute stars, planets, and living things. Physicists have proposed various candidates over the years, including weakly interacting massive particles, axions, sterile neutrinos, and primordial black holes. Experiments around the world are searching for direct evidence of dark matter particles colliding with ordinary matter, so far without definitive success. The nature of dark matter remains one of the deepest unsolved problems in all of physics, a mystery that touches on fundamental questions about what the universe is made of. In the standard cosmological model, dark matter played a crucial role in forming the first galaxies. After the Big Bang, slight variations in the density of dark matter began pulling regular matter toward certain regions of space. These became the seeds around which the first structures formed. Gas fell into these. Dark matter halos condensed and ignited the first stars. Over time, those dark matter halos merged and grew larger, bringing their galaxies along with them. The whole process was supposed to take time, hundreds of millions of years at minimum before major galaxies could assemble. But the discovery of bright, massive galaxies like JD's GSZ 14-0 in the first few 100 million years after the Big Bang creates tension with this picture. Either dark matter halos formed and grew faster than the models predict, or something else was driving early galaxy formation that scientists have not yet identified. Some researchers have proposed that star formation was simply far more efficient in the early universe. Perhaps the first stars converted gas into stellar mass at higher rates than stars do today. Perhaps feedback processes that normally slow down star formation, like supernova explosions blowing gas out of galaxies, work differently in those early conditions. The answers remain unclear. Others have suggested even more radical possibilities. Perhaps our understanding of dark energy, the mysterious force driving the accelerating expansion of the universe, needs revision. The standard model assumes dark energy has been constant throughout cosmic history. But what if it was different in the early universe? More dark energy early on could have changed the expansion rate and affected how quickly structures formed. Some theoretical models that adjust dark energy actually do predict faster galaxy formation, though these models bring their own challenges and do not perfectly fit all the available data. There are also questions about black holes. The Webb telescope has found evidence that supermassive black holes existed surprisingly early in cosmic history. These are black holes millions or billions of times more massive than our sun, sitting at the centers of early galaxies and actively consuming material. One such black hole was discovered in a galaxy that existed just 430 million years after the Big Bang. That black hole weighs about 1.6 million times the mass of the Sun and is actively growing by pulling in gas from its surroundings. The problem is that black holes are supposed to grow slowly. They form when massive stars collapse at the end of their lives, creating initial black holes maybe a few dozen times the mass of the Sun. Those seed black holes then grow over time by consuming nearby gas and merging with other black holes. But there are limits to how fast this can happen. Gas falling into a black hole releases tremendous energy in the form of light and radiation. That radiation pushes back against incoming gas, limiting how quickly the black hole can feed. Physicists call this the Eddington limit. For a black hole to grow from stellar mass to millions of solar masses in just a few 100 million years, it would need to consume material at rates pushing right up against or even exceeding this theoretical maximum. Some scientists wonder if black holes in the early universe had different starting conditions. Maybe they formed not from dying stars, but from the direct collapse of massive gas clouds, creating larger seed black holes right from the start. All of these questions feed into the broader puzzle that the James Webb Space Telescope keeps revealing. The early universe is not what scientists expected. It is brighter, more mature, more chemically complex, and more full of massive structures than the models predicted. This does not mean our basic understanding of cosmology is wrong. The core framework that the universe began in a hot, dense state and expanded over billions of years remains solid. The cosmic microwave background radiation, which is the afterglow of the Big Bang, matches the predictions of this model with incredible precision. The large-scale structure of the universe, the way galaxies cluster into webs and filaments, also matches. But something about the fine details of how galaxies and black holes assembled in the first billion years requires adjustment. Think of it like weather forecasting. Meteorologists understand the basic physics of how weather works. They can predict that winter will be cold and summer will be warm. They can anticipate that hurricanes form in tropical waters, but predicting exactly when a storm will arrive, how intense it will be, and where it will make landfall requires incredible precision. Small errors in the input data propagate and grow. The general framework is right, but the details are hard. Cosmology is similar. The general story of the universe is well established. The specific details of early galaxy formation happening over 13 billion years ago in conditions we have never directly observed until now are where the surprises lurk. The discovery of this ancient galaxy also connects to one of the most dramatic transformations in cosmic history, an era called the Epoch of Rayonization. To understand what this means, we need to go back to the very beginning of the universe. In the first few 100,000 years after the Big Bang, the universe was filled with a hot plasma of charged particles, mostly protons and electrons, flying around freely. This plasma was opaque. Light could not travel through it without immediately being scattered by the charged particles, like headlights in thick fog. But as the universe expanded and cooled, something changed. About 380,000 years after the Big Bang, the temperature dropped enough for protons and electrons to combine into neutral hydrogen atoms. Suddenly, light could travel freely. The universe became transparent for the first time. The radiation released at that moment has been traveling through space ever since, cooling and stretching as the universe expands. Today we detect it as the cosmic microwave background, a faint glow of microwaves coming from every direction in the sky. After the cosmic microwave background formed, the universe entered what astronomers call the Dark Ages. For millions of years, no stars existed. The cosmos was filled with neutral hydrogen gas, slowly cooling and condensing under the pull of gravity. There were no sources of visible light. If you could somehow visit that era, the universe would appear completely black in every direction. The only light would be the gradually fading afterglow of the cosmic microwave background, already shifted far into the infrared. Eventually, maybe 100 to 200 million years after the Big Bang, the first stars began to form. These were unlike any stars we see today, formed from pure hydrogen and helium with no heavier elements. They burned hotter and bluer than modern stars. They were probably dozens or even hundreds of times more massive than our sun. And they lived fast and died young, burning through their fuel in just a few million years before exploding in titanic supernovas. These first stars marked the end of the Dark Ages and the beginning of what astronomers call cosmic dawn. The light from these early stars had a transformative effect on the surrounding universe. That light contained enough energy to knock electrons free from hydrogen atoms, ionizing the gas. Bubbles of ionized hydrogen began forming around the first stars and galaxies, expanding outward like spheres of clarity in a foggy landscape. As more stars formed and more galaxies grew, these bubbles grew larger and began overlapping. Eventually, maybe around 1 billion years after the Big Bang, the entire universe had been reionized. The neutral hydrogen fog was gone. The cosmos became transparent to ultraviolet light for the first time since the era before stars existed. This epoch of reionization is one of the last major transitions in cosmic history that remains poorly understood. Scientists know roughly when it happened, but the details are murky. The transition from neutral to ionized gas did not happen all at once throughout the universe. Instead, it proceeded in a patchy fashion, with some regions becoming ionized earlier than others. The areas around the brightest, most active galaxies ionized first, as their powerful radiation carved out bubbles of clarity in the surrounding fog. Over time, these bubbles grew and merged, eventually percolating throughout the entire cosmos until no neutral hydrogen remained in intergalactic space. Imagine a dark room slowly filling with light from multiple sources. At first, you see only small pools of illumination around each lamp. Then, as the lamps brighten and more lamps turn on, the pools expand and begin to overlap. Eventually, the entire room is lit, and the original darkness exists only as a memory. That is roughly what happened during reionization, except the room was the entire universe, and the lamps were the first stars and galaxies coming to life. The timing of this transition matters enormously for understanding what caused it. If reionization happened quickly, it suggests that very bright, energetic sources drove the process. If it happened slowly, more gradual accumulation of smaller sources might be responsible. Recent measurements using the cosmic microwave background and observations of distant quasars suggest that reionization took several hundred million years, beginning perhaps around 400 million years after the Big Bang and wrapping up around 1 billion years later. But these are rough estimates. Webb is providing new data points that will help pin down the timeline more precisely. The sources that drove reionization remain debated. The most obvious candidates are hot young stars in early galaxies. These stars produce copious amounts of ultraviolet light, exactly the type of radiation needed to knock electrons free from hydrogen atoms. The brighter and more numerous these early galaxies were, the faster they could ionize the surrounding gas. Webb's discovery of unexpectedly bright early galaxies is therefore directly relevant to understanding reionization. If the early universe contained more luminous galaxies than previously thought, those galaxies could have driven reionization faster and more thoroughly than older models predicted. But hot stars are not the only possible sources of ionizing radiation. Growing black holes also produce intense ultraviolet and X-ray light as gas falls into their gravitational maws. In the nearby universe, quasars are among the brightest objects known, visible across billions of light years. If similar objects existed in the early universe, they could have contributed significantly to reionization. The relative contributions of stars versus black holes is one of the key questions that Webb observations are helping to resolve. By counting both early galaxies and early quasars and measuring their properties, scientists can estimate how much ionizing radiation each type of source produced. There's also the question of which types of galaxies contributed most to reionization. Large, bright galaxies are the easiest to detect, but they might not have been the most important sources. Many theoretical models suggest that small, faint dwarf galaxies were the primary drivers of reionization. These tiny galaxies might have been far more numerous than their larger cousins, and their collective radiation output could have exceeded that of the giants. The problem is that these dwarf galaxies are extremely difficult to detect directly because they are so faint. Even Webb can only see the brightest early galaxies. But by combining observations with theoretical models, scientists can estimate how many dwarf galaxies existed and how much they contributed. Gravitational lensing helps with this problem. When light from a distant galaxy passes through a massive foreground cluster, the cluster's gravity magnifies the background galaxy like a natural zoom lens. This magnification allows telescopes to see galaxies that would otherwise be too faint to detect. Webb has already found several strongly lensed galaxies from the epoch of reionization, including some that appear to be small dwarf galaxies caught in the act of ionizing their surroundings. These observations provide crucial data points for understanding the role of small galaxies in this cosmic transition. Which objects drove the process? Was it mainly hot stars and early galaxies? Or did the powerful radiation from growing black holes play an important role? How patchy was the reionization? Did it happen everywhere at once, or did some regions stay neutral longer than others? The James Webb Space Telescope is ideally suited to answer these questions because it can see galaxies from before, during, and after reionization. It can catch the universe in the act of transforming. The ancient galaxy at redshift 14.32 exists right at the frontier of this era. It existed when the universe was still mostly neutral before reionization was complete. Light from this galaxy had to punch through thick fog of neutral hydrogen to reach us. One surprising finding is that the data shows less neutral hydrogen around this particular galaxy than scientists expected. This suggests the galaxy was already carving out its own ionized bubble in the surrounding gas. Its stars were powerful enough to clear away the fog in its immediate vicinity, even at this incredibly early epoch. This provides direct evidence of how reionization worked at the smallest scales, individual galaxies burning holes in the cosmic fog. Scientists are not stopping with this one discovery. The Webb telescope continues to survey the deep universe, hunting for even more distant galaxies. In 2025, researchers announced an even more extreme find, a galaxy nicknamed MOMZ14, which stands for Mother of All Early Galaxies at redshift 14. This galaxy exists even further back, about 280 million years after the Big Bang, making it the most distant object ever detected at that time. Like its predecessor, MOMZ14 is surprisingly bright and chemically complex. It contains nitrogen and carbon, elements that require stellar processing to create. The team that discovered it called the finding a cosmic miracle. They emphasized that this is currently the most distant object known to humanity. Finding galaxies this early pushes up against the edge of what is theoretically possible. Remember, for the first 100 million years or so after the Big Bang, no stars existed at all. So any galaxy we detect from 250 or 300 million years after the Big Bang only had a window of maybe 150 million years to form its first stars, go through stellar generations, build up heavy elements, and assemble into a recognizable galaxy. That is an extremely short cosmic timeline for so much to happen. Every new discovery at these extreme distances tightens the constraints on how galaxy formation worked. There is something almost unsettling about peering this far back in time. The light we are seeing left its source when the universe was barely an infant by cosmic standards. 13.5 billion years of travel, stretching and dimming as it went, finally arriving at our instruments orbiting 1 million miles from a rocky planet that did not exist for most of that journey. When that ancient light first began its journey toward us, there was no Earth, there was no sun. Our entire solar system would not form for another 9 billion years. The Milky Way galaxy itself was still young and actively growing, consuming smaller satellite galaxies and building up its spiral structure through countless mergers and interactions. The atoms that would eventually become you and me and everyone you have ever known were scattered across the cosmos, inside stars that had not yet formed, or floating in clouds of gas between galaxies. And yet, through some remarkable chain of cosmic events, those atoms eventually came together. Stars formed and died, scattering their enriched material into space. New stars formed from that enriched gas, pulling in rocky material that condensed into planets. One of those planets, orbiting an unremarkable yellow star in a quiet corner of a spiral galaxy, developed liquid water, complex chemistry, and eventually life. That life evolved over billions of years, eventually producing a species clever enough to build telescopes and curious enough to point them at the sky. Now, that species catches photons that have been traveling since before our planet existed. We decode those photons, extract their information, and learn about a universe that is almost entirely beyond our direct experience. The ancient galaxy Webb detected will never be visited by any human spacecraft. The distances are too vast, the journey too long. Even light, the fastest thing in the universe, took over 13 billion years to make the trip. For any physical probe, the journey would take an eternity, but we do not need to physically travel to learn. The light itself carries information, encoded in its intensity, its wavelength, its spectrum. From that information, we can determine the distance to the galaxy, its mass, its chemical composition, its star formation rate, whether it hosts an active black hole, how fast its stars are moving, and countless other details. Astronomy is the science of learning from afar, of extracting knowledge from photons that cross cosmic distances to reach our instruments. The matter in that ancient galaxy, the hydrogen and oxygen and nitrogen atoms detected by Webb's spectrographs, has long since dispersed and recombined. Those specific atoms have not sat unchanged for 13 billion years. The stars in which they resided burned out long ago. Those stars exploded or shed their outer layers, releasing their contents back into the interstellar medium. New stars formed from that material, lived their own lives, and dispersed their contents in turn. The atoms cycled through generation after generation of stellar evolution, migrating through the galaxy and perhaps even being expelled into intergalactic space before being recaptured by another galaxy. The matter in that ancient galaxy, the hydrogen and oxygen and nitrogen atoms detected by Webb's spectrographs, has long since dispersed and recombined. Some of those atoms might now exist in galaxies we see in the nearby universe. Some might have ended up in stars that formed billions of years later. Tracing those individual atoms is impossible, but the idea that matter cycles through the cosmos over billions of years gives the discovery an almost personal dimension. We are made of atoms that were once part of ancient stars. Those stars might have existed in galaxies not so different from the one Webb just found. The telescope is also revealing that these early galaxies come in unexpected shapes and sizes. Classical theories predicted that the first galaxies would be small, irregular, and clumpy. They should look nothing like the elegant spiral and elliptical galaxies we see in the more recent universe. But Webb has found early galaxies with surprisingly regular disk-like structures, long, thin tubes, and flattened ovals. Some show evidence of ordered rotation, where the gas and stars are moving in organized patterns rather than chaotic swirls. These features take time to develop. Gravity needs many orbital periods to settle material into stable configurations. Finding such ordered structures just a few 100 million years after the Big Bang suggests that either galactic dynamics work faster than expected, or that our picture of early galactic chaos is too simplistic. One team of astronomers using Webb discovered 3 ultra-massive galaxies that existed within the first billion years after the Big Bang. Each of these galaxies contains almost as much stellar mass as our entire Milky Way, which took over 13 billion years to grow to its current size. The researchers found that these early massive galaxies were converting gas into stars almost twice as efficiently as later galaxies. In the modern universe, only about 20% or less of the gas in a galaxy typically ends up in stars. The rest gets heated and blown out by supernova explosions and other feedback processes. But in these ancient monsters, something was different. Star formation was running at full throttle, building up enormous stellar populations in remarkably short timeframes. The implications ripple outward into many areas of astrophysics. If early galaxies formed more stars more quickly, they would have produced more supernovas. Those supernovas would have scattered more heavy elements into the intergalactic medium earlier in cosmic history. That enriched gas would then become the raw material for the next generation of stars and galaxies. The timing of chemical enrichment matters enormously for the eventual emergence of planets and life. Rocky planets like Earth require elements heavier than hydrogen and helium to form. Our planet's iron core, silicon-rich mantle, and oxygen-rich crust all depend on elements that were forged inside stars and dispersed by stellar explosions. The carbon in your body, the nitrogen in your DNA, the calcium in your bones, none of these existed at the beginning of the universe. Every atom heavier than lithium had to be created through stellar nucleosynthesis, either in the cores of living stars or in the cataclysmic explosions of dying ones. If the universe started cooking up these essential elements earlier than scientists previously thought, it could push back the timeline for when habitable planets first became possible. Perhaps rocky planets capable of supporting liquid water chemistry existed much earlier in cosmic history than current models predict. Perhaps the conditions for life arose in the universe billions of years before they arose on Earth. These are speculative possibilities, but they follow logically from the discovery that chemical enrichment happened faster than expected. The carbon and oxygen detected in those ancient galaxies are particularly significant in this context. Carbon is the basis of organic chemistry, the framework on which the molecules of life are built. Its ability to form 4 chemical bonds makes it uniquely suited for constructing the complex molecules that biology requires. Oxygen is essential for water, the solvent in which life on Earth evolved and continues to operate. Finding substantial amounts of both elements in galaxies less than 300 million years old suggests that the chemical prerequisites for life were being assembled very early in cosmic history. Of course, having the right elements is only the first step. Life also requires the right environment, the right energy sources, the right timescales for complex chemistry to develop. A galaxy might contain carbon and oxygen without containing any planets suitable for life. The conditions on early Earth that allowed life to emerge, liquid water oceans, a stable climate, protection from lethal radiation, took billions of years to establish even after the solar system formed. There is no reason to think life could have arisen immediately after the first heavy elements appeared. But the discovery does expand the window of possibility. If carbon and oxygen were widespread 300 million years after the Big Bang, then the potential for life chemistry has existed for over 13 billion years. Our solar system formed only about 4.5 billion years ago. That means life had roughly 9 billion years of cosmic history before us, in which to potentially arise somewhere else. Whether it actually did so is unknown and perhaps unknowable, at least with current technology. But the existence of that vast expanse of prior time, filled with the necessary chemical ingredients, is a thought-provoking consequence of Webb's discoveries. There's also the question of what role early galaxies played in shaping the intergalactic medium, the thin gas that fills the vast spaces between galaxies. This gas is not empty vacuum. It contains trace amounts of hydrogen, helium, and heavier elements, along with radiation fields and magnetic fields that permeate the cosmos. The intergalactic medium contains a record of cosmic history, a chemical journal written across billions of years of stellar evolution and galactic activity. Radiation from early stars and black holes left signatures in this gas. The ultraviolet photons that drove reionization ionized hydrogen atoms and left the intergalactic medium in its current ionized state. The heavy elements scattered by supernovas ended up here, slowly mixing into the primordial hydrogen and helium. By studying distant quasars and measuring how their light gets absorbed by intervening gas at various redshifts, astronomers can reconstruct the conditions at different epochs of cosmic history. The findings from Webb are now informing these studies, providing crucial context for interpreting what kinds of objects were producing the radiation and elements detected in the intergalactic medium. If early galaxies were brighter and more numerous than previously thought, that changes the expected ionization state of the gas at various times. If chemical enrichment proceeded faster than models predicted, that changes the expected abundance of heavy elements in the intergalactic medium at high redshifts. The different strands of evidence must all fit together into a coherent picture. This interconnectedness is one of the beautiful aspects of modern astrophysics. No observation exists in isolation. Everything connects to everything else. The properties of early galaxies affect the state of the intergalactic medium, which affects the formation of later galaxies, which affects the distribution of matter in the present-day universe, which affects what we observe in our cosmic neighborhood. Tracing these connections across billions of years of cosmic evolution is the grand challenge that drives the field forward. The timing of chemical enrichment matters for everything from the formation of rocky planets to the eventual emergence of life. Planets like Earth need elements heavier than hydrogen and helium to form: iron for our cores, silicon for our rocks, carbon for our chemistry. If the universe started cooking up these elements earlier than we thought, it could push back the timeline for when habitable planets first became possible. There is also the question of what role early galaxies played in shaping the intergalactic medium, the thin gas that fills the space between galaxies. That gas contains a record of cosmic history, like a chemical journal written across billions of years. Radiation from early stars and black holes left signatures in this gas. The heavy elements scattered by supernovas ended up here. By studying distant quasars and measuring how their light gets absorbed by intervening gas, astronomers can reconstruct the conditions at different epochs. The findings from Webb are now informing these studies, providing context for what kinds of objects were producing the radiation and elements detected in the intergalactic medium. Some of the most exciting discoveries involve cases where the universe acts as a natural magnifying glass. When light from a distant galaxy passes near a massive foreground object like a galaxy cluster, gravity bends the light and focuses it. This effect is called gravitational lensing, and it was first predicted by Albert Einstein over a century ago as a consequence of his general theory of relativity. The basic principle is straightforward. Mass warps the fabric of space-time, and light follows the curved paths through that warped space-time. When a massive object like a galaxy cluster sits between us and a more distant source, the light from that source gets bent around the intervening mass. If the geometry is right, the bending can focus the light, making the distant source appear brighter and larger than it otherwise would. In some cases, gravitational lensing can magnify a distant galaxy by factors of 10, 20, or even more. This allows telescopes to see details that would otherwise be impossible to detect, even with the most powerful instruments. It is like suddenly having access to a telescope with a mirror many times larger than anything we could actually build. Nature provides the extra magnification for free, though finding suitable lens systems requires careful observation and analysis. Webb has found several extremely distant galaxies that are strongly lensed by foreground clusters. In some of these systems, the magnification is high enough to reveal individual star-forming regions within the distant galaxies. This is extraordinary. Without lensing, those galaxies would appear as faint smudges even in Webb's deepest images. With lensing, they become laboratories for studying the detailed physics of star formation in the early universe. One particularly striking example revealed dense clusters of young stars forming in an ancient galaxy during the epoch of ionization. These protoglobular clusters, as scientists call them, are packed with stars at densities hundreds of times greater than typical star-forming regions in modern galaxies. Globular clusters today are some of the oldest known structures in the universe, containing stars over 10 billion years old, orbiting the outskirts of galaxies like ancient fossils. Seeing the formation of such clusters happening in real time during the first billion years of cosmic history connects the present to the past in a visceral and immediate way. The ancestors of the globular clusters orbiting our own Milky Way might have formed in conditions exactly like what Webb is observing in these distant lensed galaxies. Those ancient clusters have orbited our galaxy for over 12 billion years, their stars slowly aging but still burning with the same nuclear fires that ignited in the early universe. When you look at a globular cluster through a backyard telescope, you are seeing a relic of cosmic dawn, a structure that formed when the universe was young and has survived essentially unchanged ever since. The connection between what Webb observes at extreme distances and what exists in our local cosmic neighborhood is a recurring theme in these discoveries. The universe has been around for almost 14 billion years, and the matter and energy that existed at the beginning has been cycling through stars, galaxies, and the spaces between them ever since. Nothing is truly isolated. Everything is connected across the vast scales of cosmic space and time. Consider again those oxygen atoms detected in the ancient galaxy at redshift 14. Each of those atoms was forged in the core of a massive star under pressures and temperatures beyond anything we can create in laboratories on Earth. When that star exhausted its fuel and exploded as a supernova, the oxygen scattered into the surrounding gas. Some of it might have been incorporated into new stars. Some might have drifted through the intergalactic medium for billions of years. The galaxy that produced those oxygen atoms might have merged with other galaxies, grown larger, changed shape, moved through the cosmic web of dark matter filaments. By now, 13 billion years later, those original oxygen atoms could be essentially anywhere in the observable universe. They might be part of a star in a distant galaxy. They might be floating in intergalactic space. They might, through an extraordinarily unlikely chain of events, have ended up in a planet orbiting a star in some corner of the cosmos where conditions allowed complex chemistry to develop. The atoms you're made of have similar histories. They were forged in stars, scattered by explosions, cycled through multiple generations of stellar evolution, before eventually ending up in the gas cloud that collapsed to form our solar system. This is the cosmic perspective that discoveries like Webb's ancient galaxy reinforce. We are not separate from the universe. We are part of it. The same physical processes that built galaxies 13 billion years ago are still operating today. The same nuclear reactions that forged heavy elements in the early cosmos forge them in stars right now. The same gravitational forces that assembled the first structures continue to shape the distribution of matter across the universe. We are participants in an ongoing cosmic drama that began long before Earth existed and will continue long after our species is gone. In some cases, lensing can magnify a distant galaxy by factors of 10, 20, or even more, allowing telescopes to see details that would otherwise be impossible to detect. Webb has found several extremely distant galaxies that are strongly lensed, including some with magnifications high enough to reveal individual star-forming regions within the galaxies. This is like suddenly having access to a telescope with a mirror 10 times larger than anything we could actually build. Nature provides the extra magnification for free. One particularly striking lensed observation revealed dense clusters of young stars forming in an ancient galaxy during the epoch of Rayonization. These proto-globular clusters, as scientists call them, are packed with stars at densities hundreds of times greater than typical star-forming regions in modern galaxies. Globular clusters today are some of the oldest known structures in the universe, containing stars over 10 billion years old orbiting the outskirts of galaxies like ancient fossils. Seeing their formation happening in real time during the first billion years of cosmic history connects the present to the past in a visceral way. The ancestors of the globular clusters orbiting our own Milky Way might have formed in conditions exactly like what Webb is observing in these distant lensed galaxies. The telescope has also been investigating the mysterious connection between galaxies and the supermassive black holes at their centers. Nearly every large galaxy in the nearby universe hosts such a black hole, and there seems to be a tight relationship between the mass of the black hole and the properties of its host galaxy. Larger galaxies have larger black holes. This correlation suggests that black holes and galaxies grow together, influencing each other over cosmic time. But which came first? Did the galaxy form first and then develop a black hole at its center? Or did black hole seeds form early and then pull in gas to build the surrounding galaxy? Webb is finding evidence that black holes were already substantial in the earliest galaxies, suggesting they might play a more fundamental role in early galaxy formation than previously appreciated. The radiation from these early black holes could have helped drive ionization. When gas falls into a black hole, it gets superheated and releases intense radiation, including ultraviolet and X-ray light. This radiation can ionize hydrogen just like starlight can. If early black holes were active enough, they might have contributed significantly to burning away the neutral hydrogen fog after the dark ages. Disentangling the contributions of stars versus black holes to ionization is one of the open questions Webb is helping to address. Every new detection of an early galaxy or early black hole adds another data point to this puzzle. The discoveries are coming faster than scientists can fully analyze them. The Webb telescope generates terabytes of data, and the worldwide astronomical community is racing to process and interpret it all. New papers appear weekly announcing detections of record-breaking galaxies, unusual chemical abundances, unexpected structures, and other surprises. The learning curve is steep. Techniques for analyzing Webb data have to be invented and refined on the fly. Calibration of the instruments continues to improve as scientists gain experience with their behavior. Some early claims about extremely distant galaxies have had to be revised as better. Data came in. That is how science works. Initial estimates get refined and corrected as more information becomes available. The process of scientific discovery is rarely as clean and linear as textbooks sometimes suggest. Real science involves false starts, dead ends, revised conclusions, and constant questioning. When Webb first started returning images, the astronomical community was flooded with preprints claiming detections of galaxies at extreme redshifts. Some of these claims were based on photometric estimates, where the distance to a galaxy is inferred from the colors of its light, rather than from a detailed spectrum. Photometric redshifts are useful for surveying large numbers of objects quickly, but they can be fooled by certain types of galaxies at intermediate distances that mimic the colors of much more distant objects. As spectroscopic follow-up observations rolled in, some of the most extreme distance claims had to be walked back. Galaxies that had been estimated to exist within the first 200 million years of cosmic history turned out to be somewhat closer, existing perhaps 400 or 500 million years after the Big Bang. That is still extremely early and scientifically valuable. But the initial excitement about potentially finding galaxies from the very first moments of cosmic dawn was tempered. The community learned to be more careful about distinguishing between photometric candidates and spectroscopically confirmed detections. This self-correcting nature of science is actually one of its greatest strengths. Unlike belief systems that resist change, science welcomes challenges and revisions. When new data contradicts a previous conclusion, scientists do not dig in and defend the old answer. They update their understanding based on the new evidence. The goal is not to be right all the time, but to be less wrong over time. Each correction brings the scientific consensus closer to reality. The confirmed detections from Webb, like JADE's GSZ 14-0, have passed through this gauntlet of scrutiny. The spectroscopic data leaves no room for confusion about the distance. The emission and absorption features in the spectrum unambiguously place this galaxy at redshift 14.32, corresponding to about 290 million years after the Big Bang. This is not an estimate or a guess. It is a measurement, as reliable as any measurement can be in observational astronomy. And the implications of that measurement are forcing theorists to reconsider aspects of their models. The interplay between observation and theory is the engine that drives progress in astrophysics. Observers collect data about what the universe actually looks like. Theorists build models that try to explain those observations and predict what future observations should find. When observations match predictions, the models are confirmed. When observations disagree with predictions, the models need revision. Right now, the early galaxy observations from Webb are in the second category. The models did not predict this many bright, massive, chemically complex galaxies this early in cosmic history. Something in the models needs to change. Several possibilities are being explored. Perhaps the initial mass function of stars in the early universe was different than it is today, weighted more heavily toward massive stars that produce more light per unit of stellar mass. Perhaps the efficiency with which gas turns into stars was higher in primordial conditions, before feedback processes from previous stellar generations had time to establish themselves. Perhaps the role of dark matter in seeding early structure formation was somehow enhanced in ways the current models do not capture. Perhaps even more exotic physics is at play, involving properties of dark energy or dark matter that deviate from the standard assumptions. Each of these possibilities makes different predictions about other observable quantities. If the initial mass function was different, that should affect the chemical abundances produced by early supernovas. If star formation efficiency was higher, that should leave signatures in the structure of early galaxies. If dark matter behaves differently than expected, that might show up in the clustering patterns of early galaxies. By gathering more data and testing these predictions, scientists can narrow down which explanations are most likely correct. This is the process that Webb is enabling on an unprecedented scale. Before Webb, astronomers had only a handful of confirmed galaxies from the first billion years of cosmic history. The statistics were too poor to distinguish between different theoretical scenarios. Now, with dozens of confirmed early galaxies and hundreds of candidates, the statistics are improving rapidly. The distributions of masses, luminosities, star formation rates, and chemical abundances are becoming measurable. Theorists can compare their model predictions to these distributions and see where the models succeed and where they fail. The next few years will be crucial for this enterprise. Webb will continue to survey the deep universe, building larger and larger samples of early galaxies. Follow-up spectroscopy will confirm distances and measure properties for the most interesting candidates. New analysis techniques will extract more information from the data, and theorists will race to update their models to match the emerging picture. By the end of the decade, our understanding of the first billion years of cosmic history could look very different than it does today. But the overall picture remains astonishing. The universe formed complex structures faster than anyone expected. Galaxies with billions of solar masses appeared within the first few 100 million years. Black holes reached millions of solar masses in that same window. Heavy elements accumulated to levels that should have taken longer. Ordered galactic structures emerged from primordial chaos more quickly than models predicted. The standard cosmological framework is probably not broken, but it clearly needs refinement. The physics that governs early galaxy formation contains factors that were underestimated or misunderstood. Webb is providing the data needed to figure out where the models went wrong. And this is just the beginning. The telescope was designed to operate for at least 10 years with enough fuel to potentially last 20 years or more. Every year will bring deeper observations, better calibrated instruments, and more refined analysis techniques. Scientists are already planning next-generation surveys that will push even further back toward the first stars. They are developing new algorithms to extract the faintest possible signals from the data. Theorists are building new models that incorporate the lessons learned from Webb's early discoveries. The coming decade will transform our understanding of cosmic dawn. For those of us watching from Earth, there is something profound about these discoveries. They connect us to a past so distant that human minds struggle to grasp the timescales involved. Light that left an ancient galaxy over 13 billion years ago, traveling through an ever-expanding universe, finally arriving at a telescope that our species designed and built, and launched into space. We are tiny creatures on a small planet, orbiting an ordinary star in an average galaxy. Yet we have found ways to peer back to nearly the beginning of everything and to piece together the story of how the cosmos evolved into what we see today. The achievement is not just scientific, but also deeply human. Throughout history, people have looked up at the night sky and wondered what was out there. Ancient civilizations mapped the stars, tracked the movements of planets, and wove stories to explain the celestial patterns they observed. The impulse to understand the universe seems to be built into our species. We cannot help asking questions about where we came from and what our place is in the grand scheme of things. For most of human history, these questions remained unanswerable. The stars were mysterious lights whose true nature was unknown. The scale of the universe was unimaginable. The idea that galaxies existed beyond our own Milky Way was not established until the 1920s, less than a century ago. The Big Bang Theory, which describes the origin and evolution of the universe, was developed and refined over the 20th century through the work of countless scientists building on each other's discoveries. Now, in the 21st century, we have instruments capable of seeing the universe as it was when it was barely more than an infant. The journey from ancient stargazers to the James Webb Space Telescope represents thousands of years of accumulated knowledge, each generation learning from and building upon the work of those who came before. The telescope itself is a monument to human curiosity and collaboration, involving contributions from thousands of people across multiple nations working toward a shared goal of understanding the cosmos. And what they have found exceeds expectations. The early universe is not the quiet, simple place that some models predicted. It is active, dynamic, chemically complex, and full of structures that challenged assumptions about how galaxies form and grow. Every new observation raises new questions. Every answer opens doors to deeper mysteries. That is the nature of scientific exploration. The more we learn, the more we realize how much remains unknown. But that unknown is not frustrating, it is inviting. It beckons us to keep looking, keep questioning, keep building better instruments and developing better theories. The discoveries from Webb are not the end of a story, but the beginning of a new chapter. The telescope will continue operating for years, perhaps decades, and each year will bring new revelations. Future observatories will push even further, perhaps detecting the very first stars ever to form, or the gravitational waves from primordial processes in the earliest moments after the Big Bang. The quest to understand the universe has no finish line. There is always more to discover, always another horizon beyond the current one, always deeper questions lurking beneath the answers we have found. That endless frontier is what makes science so compelling and so worthy of the resources and effort we invest in it. The James Webb Space Telescope represents our generation's contribution to this eternal quest. What it has shown us about the ancient universe will inform scientific understanding for generations to come. That ancient galaxy, JADE's GSZ 14-0, represents just one thread in the vast tapestry of cosmic history, but it is a crucial thread, a key piece of evidence in the puzzle of how our universe came to be. It tells us that the universe was already busy building complex structures when it was barely old enough to have formed stars at all. It tells us that our models of early galaxy formation need substantial revision and refinement. It tells us that there are probably even more distant galaxies waiting to be found, galaxies that formed even closer to the very beginning of cosmic time. And it tells us that the James Webb Space Telescope, orbiting silently 1,000,000 miles from Earth with its gold-plated mirrors catching light from the edge of time, is going to keep delivering revelations and reshaping our understanding of the cosmos for many years to come. There really is no going back from this. Once you know that galaxies existed 13 billion years ago, and that they were brighter, more massive, and more chemically complex than expected, you cannot unsee that knowledge. The models will have to change, the textbooks will have to be rewritten, and our picture of the early universe will continue to sharpen as more discoveries roll in. This is what science looks like at its best, not a static collection of facts, but a living, evolving enterprise where new observations constantly challenge and refine our understanding. The cosmos keeps surprising us, and that is exactly what makes exploring it so worthwhile. The search continues. Webb keeps watching. And somewhere out there in the darkness of space, the light from even more ancient galaxies is still traveling toward us, carrying secrets from the dawn of time. Scientists often describe the feeling of making a major discovery as a mix of excitement and disbelief. When the team analyzing JADE's GSZ 14-0 first processed the spectroscopic data confirming its extreme distance, some of them could not believe what they were seeing. The spectrum was unmistakable. The redshift measurement was solid, but the implications felt almost too dramatic. Here was a galaxy that shattered the previous distance record, and it was doing so while being unexpectedly bright and massive. The researchers exchanged messages with lots of exclamation marks, as one of them later described. It was one of those rare moments in science when you know immediately that what you have found will change how people think about the universe. Part of what makes this discovery so compelling is how it connects to larger questions about our place in the cosmos. Humans have always wondered where we came from, not just as individuals or as a species, but as inhabitants of a universe with a beginning and a history. The Big Bang gave us a starting point. Cosmic expansion gave us a framework. But the details of how the first stars and galaxies formed, how the elements that make up our bodies were synthesized, how the conditions for life arose, these remained fuzzy. Each new discovery from Webb brings those details into sharper focus. Consider the oxygen detected in that ancient galaxy. Every oxygen atom has a history. It was once inside a massive star, fusing from lighter elements in the crushing pressure of the stellar core. When that star exploded, the oxygen scattered into space. Eventually, it became part of new gas. Clouds, new stars, new planets. The oxygen you breathe right now went through that process somewhere in the Milky Way's history. And the oxygen in Jade's GSS 14-0 represents one of the earliest examples of that process, happening anywhere in the universe. Those atoms were forged in the fires of some of the first stars ever to exist. There is a continuity here that stretches across billions of years. The first stars lived and died, scattering their creations into the cosmos. New generations of stars formed, incorporating those heavier elements, living their own lives, and eventually scattering their products in turn. Galaxies grew and merged, stars migrated, gas cycled between stars and the spaces between them. And eventually, after over 9 billion years of this cosmic churning, a small rocky planet formed around a young yellow star in a quiet arm of an ordinary spiral galaxy. That planet would eventually support life, and that life would eventually build telescopes capable of seeing back to when the whole process started. This is the story the James Webb Space Telescope is helping us tell, not just a catalog of distant objects, but a narrative of cosmic evolution that leads directly to our own existence. Every early galaxy detected by Webb is an ancestor in a very real sense. The atoms in our bodies trace back through a chain of stellar and galactic events stretching to the earliest epochs. We are quite literally made of material that once existed in galaxies like the ones Webb is now observing. The telescope is also revealing just how active and violent the early universe was. Those first generations of stars were not gentle, long-lived suns like ours. They were titans, dozens or hundreds of times more massive, burning through their fuel in just a few million years. When they died spectacularly, in explosions that briefly outshone entire galaxies. These supernovas were the forges that built the elements heavier than helium. Each explosion was a blast of nuclear creation, transforming lighter atoms into heavier ones and flinging them across space at thousands of miles per second. The rate of supernova explosions in the early universe would have been astounding by modern standards. In a young, actively star-forming galaxy like those Webb is detecting, massive stars would be reaching the ends of their brief lives constantly. Explosions would punctuate the galactic environment every few thousand years or less. Shockwaves from these explosions would ripple through the interstellar gas, triggering new episodes of star formation while simultaneously blowing some gas out of the galaxy entirely. The interplay between star formation and supernova feedback is one of the key factors that regulates how galaxies grow. Getting this balance right in theoretical models is notoriously difficult, and Webb's observations are providing new calibration points for these models. Black holes added another layer of activity to this early cosmic scene. When gas falls into a black hole, the gravitational energy released generates tremendous radiation. This radiation can heat surrounding gas, preventing it from cooling and condensing into new stars. But it can also drive powerful winds and jets that reach far beyond the immediate vicinity of the black hole, affecting the gas throughout an entire galaxy and even into the intergalactic medium. These feedback processes from black holes are thought to be crucial for regulating the growth of the most massive galaxies. Without feedback, galaxies would convert too much of their gas into stars too quickly, ending up much more massive than we actually observe. The balance between all these processes, star formation, supernova feedback, black hole feedback, and gas inflows and outflows, determines the ultimate properties of a galaxy. Getting this balance wrong in computer simulations leads to predictions that do not match observations. For decades, astronomers have been refining their models to better reproduce the galaxy population we see in the nearby universe. But now Webb is providing a new test. The models also have to reproduce what we see in the very early universe. And so far, many models are struggling to explain the abundance and brightness of the earliest galaxies Webb is detecting. This does not mean the models are completely wrong. It means they are missing something. Perhaps the efficiency of star formation in pristine primordial gas was higher than assumed. Perhaps the first black holes formed from more massive seeds than typically modeled. Perhaps some aspect of the physics, like the way radiation interacts with dust, works differently under the extreme conditions of the early universe. Theorists are exploring all these possibilities and more. The interplay between new observations and new theory is what drives progress in astrophysics. One particularly intriguing possibility involves the very first stars, known as population 3 stars. These theoretical objects have never been directly observed. They are thought to have formed from pure hydrogen and helium, without any of the heavier elements that exist in later stellar generations. The absence of heavy elements changes the physics of star formation in important ways. Heavy elements help gas cool more efficiently, allowing it to collapse into smaller, denser clumps that become normal mass stars like our Sun. Without those coolants, the first stars had to cool through different, less efficient channels, resulting in much more massive stars. If population 3 stars were indeed very massive, they would have lived fast, died young, and exploded with tremendous energy. Their explosions might have been different from typical supernovas, potentially leaving behind unusual remnants or dispersing unusual element ratios. Some theorists have speculated that very massive population 3 stars might have collapsed directly into black holes at the end of their lives without exploding at all. These direct collapse black holes could have been the seeds from which the first supermassive black holes grew. If this picture is correct, then the early black holes detected by Webb might be the direct descendants of population 3 stellar evolution. Webb has the potential to eventually detect population 3 stars directly, or at least detect galaxies whose light is dominated by population 3 stellar populations. The signature would be distinctive, a particular pattern in the light spectrum that reflects the unique properties of metal-free stars. So far, no definitive detection has been made, but the search continues. Finding population 3 stars or their immediate successors would be a landmark discovery, confirming theoretical predictions that have been made for decades, and providing direct insight into the very first chapter of stellar evolution. The search for extremely early objects also overlaps with the search for gravitational waves. Gravitational waves are ripples in space-time caused by massive objects accelerating, like 2 black holes spiraling together and merging. Ground-based detectors like LIGO and Virgo have already detected gravitational waves from merging black holes and neutron stars. But these detectors are sensitive to objects in a certain mass range, roughly from a few solar masses to a few hundred solar masses. The supermassive black holes in galactic centers, millions to billions of solar masses, produce gravitational waves at different frequencies that require different detectors. Space-based gravitational wave observatories like the planned LISA mission will be sensitive to the mergers of supermassive black holes. These mergers are expected to have happened throughout cosmic history as galaxies collided and their central black holes eventually spiraled together. Detecting these mergers will provide a completely different view of cosmic evolution, one based on mass and gravity rather than light and radiation. Combined with Webb's observations of early galaxies and their black holes, the gravitational wave data will build a more complete picture of how the most massive structures in the universe grew over time. There is something almost symphonic about the way different types of observations complement each other. Radio telescopes probe cold neutral hydrogen in the intergalactic medium. Optical and infrared telescopes like Webb see the light from stars and heated gas. X-ray telescopes detect the hottest, most energetic environments around black holes. Gravitational wave detectors sense the vibrations of space-time itself. Each instrument sees a different aspect of the same cosmic reality. Putting all these perspectives together is like listening to an orchestra rather than a single instrument. The full richness of the cosmic symphony only emerges when you can hear all the parts. The James Webb Space Telescope is one of the most important instruments humanity has ever built for understanding the universe, but it does not operate in isolation. It is part of a global effort involving thousands of scientists, engineers, and support staff. The data it collects is shared with researchers around the world who analyze it using software and theoretical frameworks developed over decades. The discoveries it enables build on centuries of prior astronomical work, from Galileo's first telescopic observations to Hubble's deep field images. Each generation of astronomers stands on the shoulders of those who came before, and the quest will continue beyond Webb. Already, astronomers are planning next-generation observatories that will push the boundaries even further. The extremely large telescope being built in Chile will have a mirror nearly 40 meters across, dwarfing any existing optical telescope. Future space-based observatories are being designed to study cosmic evolution with even greater precision. New radio telescopes are coming online that will map the structure of the early universe in unprecedented detail. Each new instrument opens new windows on the cosmos. The discovery of ancient galaxies like JD's GSZ 14-0 is not the end of a story. It is a chapter in an ongoing adventure of exploration and discovery. Every answer raises new questions. Every solved puzzle reveals a deeper mystery underneath. That is the nature of science and the nature of the universe itself. We will never reach a point where we know everything. But we can keep learning, keep questioning, keep looking outward into the darkness and wondering what else is waiting to be found. For now, we know this much. The universe formed structures earlier and faster than expected. Galaxies appeared within a few 100 million years of the Big Bang that rival the complexity and mass of galaxies billions of years old. The early cosmos was not a quiet, empty void slowly filling with light. It was a busy, dynamic place where stars ignited, exploded, and scattered the seeds of future generations. Black holes grew, galaxies merged, and the neutral fog of the dark ages was burned away by the rising light of cosmic dawn. And from that ancient chaos, through billions of years of cosmic evolution, we emerged, creatures made of stardust, living on a planet made of stardust, orbiting a star made of stardust, in a galaxy made of stardust. Looking out at the cosmos with telescopes of our own design, trying to understand where it all began. That is the story the James Webb Space Telescope is helping us tell, and it is a story that belongs to all of humanity. But let us take a step back and appreciate just how remarkable the engineering achievement of the James Webb Space Telescope truly is. This was not just another telescope project. It was one of the most ambitious and challenging engineering endeavors in human history. A project that stretched over more than 2 decades, involved thousands of engineers and scientists across multiple countries, and faced repeated setbacks and delays that at times threatened to cancel the entire mission. The idea for the James Webb Space Telescope traces back to the late 1980s. Astronomers were already thinking about what would come after the Hubble Space Telescope, which had not even launched yet. They envisioned a telescope that could see in infrared wavelengths, allowing it to peer through dust, clouds, and detect the most distant objects in the universe. The concept evolved over years of studies and design work. By 1996, NASA officially began developing what was then called the Next Generation Space Telescope. The name was changed in 2002 to honor James Webb, the NASA administrator who led the agency through the critical early years of the Apollo program in the 1960s. From the beginning, the technical requirements were daunting. The telescope needed a mirror far larger than anything previously flown in space, but it also needed to be lightweight enough to launch on available rockets. The solution was a segmented mirror that could fold up for launch and unfold in space. But folding mechanisms create points of potential failure. Each segment had to deploy perfectly and then be aligned with nanometer precision. No one had ever done anything like this before. The telescope also needed to stay extremely cold. Infrared light is essentially heat radiation. Any warm object glows in infrared. If the telescope itself was warm, it would outshine the faint, distant galaxies it was trying to observe, like trying to see stars while standing next to a floodlight. The solution was a tennis court-sized sun shield made of 5 layers of thin, reflective material. This sun shield would block light and heat from the sun, earth, and moon, keeping the telescope in permanent shadow where it could cool to temperatures far below anything found naturally on Earth. But the sun shield created its own challenges. It was far too large to launch in its deployed configuration. It had to fold up into a compact package for launch and then unfold in space through a series of precisely choreographed steps. There were over 300 single-point failures in the deployment sequence, meaning 300 things that had to work perfectly or the mission would fail. Engineers spent years testing and refining the deployment mechanisms. They practiced the unfolding sequence over and over in ground-based simulations, working out every possible problem. The launch itself was a nerve-wracking moment. On Christmas Day 2021, an Ariane 5 rocket lifted off from French Guiana carrying the folded telescope. The launch had to be nearly perfect because any vibration or shock could damage the delicate optics. The telescope rode the rocket for about half an hour before separating and beginning its journey to its final orbit 1 million miles from Earth. But the real tension came in the days and weeks that followed as the unfolding sequence began. First, the solar array deployed to provide power. Then, the communications antenna unfolded. Then came the sunshield deployment, the most complex and nerve-wracking part of the entire sequence. Over several days, dozens of mechanisms fired in sequence, releasing latches and tensioning cables, gradually spreading the 5 sunshield layers into their final configuration. Engineers watched telemetry data anxiously, cheering with each successful step. When the sunshield finally reached full deployment, there were tears in mission control. Then came the mirror deployment. The 2 side sections of the primary mirror, which had been folded back like wings, swung into position and locked in place. The secondary mirror, mounted on a long boom in front of the primary, extended outward. All 18 primary mirror segments began their initial alignment. Over the following weeks, engineers sent commands to tiny motors behind, each mirror segment adjusting their positions with incredible precision until all 18 segments worked together as a single unified mirror. By February 2022, the telescope had reached its orbital destination at the second Lagrange point. By spring, the instruments were fully cooled and calibrated. In July, NASA released the first full-color science images, and the world gasped. The pictures were sharper, deeper, and more detailed than anything humanity had ever seen before. Galaxies that appeared as fuzzy blobs in Hubble images suddenly revealed intricate spiral arms and companion galaxies. Stars that had been hidden behind curtains of dust blazed forth in infrared glory. The universe looked different through the eyes of Webb, and scientists immediately began making discoveries. The first major deep field image showed a galaxy cluster called SMACS 0723. The cluster's gravity bent and magnified light from more distant galaxies behind it, creating a natural zoom lens. In that single image, astronomers spotted galaxies at extreme redshifts, candidates for the most distant objects ever seen. Follow-up spectroscopy confirmed that several of these galaxies existed within the first billion years of cosmic history. The floodgates were open. Within weeks, teams around the world were publishing papers about early galaxies detected by Webb, each one pushing back the boundaries of known cosmic history. The pace of discovery has not slowed since then. In its first year of operations, Webb observed everything from asteroids in our own solar system to galaxies at the edge of the observable universe. It detected atmospheric molecules on planets orbiting distant stars, providing clues about whether those worlds might support life. It revealed the chemical composition of interstellar dust clouds, the nurseries, where new stars and planets are born. It captured images of young stars shooting jets of gas across trillions of miles of space, and it kept finding ancient galaxies that challenged expectations. One of the most photographed Webb images is the Carina Nebula, a vast cloud of gas and dust about 7,600 light-years from Earth. In visible light, the nebula appears as a hazy glow punctuated by bright stars. But Webb's infrared vision pierced the obscuring dust to reveal hundreds of previously hidden baby stars. The image looked like a jagged mountain ridge topped with sparkling lights, and it quickly became one of the most iconic space photographs ever taken. It demonstrated both the telescope's power and its ability to see what other instruments cannot. Another famous Webb observation targeted the Southern Ring Nebula, a dying star surrounded by expanding shells of gas. Webb revealed intricate structures within the nebula, including evidence of a hidden companion star that had influenced how the dying star shed its outer layers. This was unexpected. The interaction between the two stars had sculpted the nebula into patterns that astronomers had not anticipated. It was a reminder that even well-studied objects can harbor surprises when seen in new wavelengths with new instruments. Perhaps the most dramatic early Webb image showed Stephan's Quintet, a grouping of 5 galaxies located about 290 million light-years away. The image covered an area of sky equivalent to about 1/5 the diameter of the full moon. It contained over 150 million pixels and required 1,000 individual image files to assemble. The quintet actually consists of 4 galaxies that are gravitationally interacting with each other, plus a 5th galaxy that happens to lie in the foreground. Webb revealed shockwaves from the collisions between galaxies, streams of stars pulled out by gravitational tides, and brilliant cores where supermassive black holes are actively feeding on and falling gas. These early showcase images demonstrated what Webb could do. But the real scientific payoff comes from the systematic surveys and targeted observations that make up the bulk of the telescope's science program. Teams of astronomers compete for observing time, proposing specific observations that address scientific questions. A committee reviews the proposals and allocates time to the most compelling ones. Every hour of Webb time is precious. The telescope can only look at one small patch of sky at a time, and the list of things worth observing is essentially infinite. Prioritizing is essential. The JADIS program that discovered JADIS GSZ 14-0 was one of these carefully planned surveys. The team received guaranteed observing time as part of the agreements that allowed various institutions to contribute to building the telescope's instruments. They used that time to stare deeply at two patches of sky previously studied by Hubble, the Goods South and Goods North deep fields. By pointing at the same patches for extended periods, they built up extremely deep images that reveal the faintest possible objects. It was in these images that the record-breaking ancient galaxy first appeared. But JADES is just one of many deep field programs underway with Webb. Other teams are surveying different patches of sky, using different strategies, and looking for different types of objects. Some are focusing specifically on gravitationally lensed galaxies, where the magnification from foreground clusters allows them to see even fainter and more distant sources. Others are conducting spectroscopic surveys, obtaining detailed spectra for hundreds of galaxies to measure their chemical compositions and star formation rates. Still others are hunting for specific types of objects, like quasars or metal-poor galaxies or unusual transient phenomena. The cumulative effect of all this work is a rapidly expanding census of the early universe. 3 years ago, astronomers knew of only a handful of galaxies at redshifts above 10. Today, the catalog includes dozens of confirmed high redshift galaxies and hundreds more candidates, awaiting spectroscopic confirmation. The statistics are improving. Scientists can now start doing population studies, asking questions not just about individual remarkable objects, but about the properties of early galaxies as a whole. What is the distribution of masses? How does star formation rate vary with mass and redshift? What fraction of early galaxies host active black holes? These statistical questions require large samples, and Webb is rapidly building those samples. The discoveries about early massive galaxies have particular implications for cosmology, the study of the universe as a whole. The standard cosmological model, often called lambda CDM, describes a universe dominated by dark energy and cold dark matter. This model has been spectacularly successful at explaining observations ranging from the cosmic microwave background to the large-scale distribution of galaxies. It predicts how structures should form and grow over cosmic time, starting from tiny density fluctuations in the early universe and gradually building up into the galaxies, clusters, and superclusters we see today. But the details of galaxy formation within this framework are uncertain. The basic gravitational physics is well understood, but the messy astrophysics of gas dynamics, star formation, supernova feedback, and black hole growth introduces complications. Computer simulations that try to model galaxy formation have to make simplifying assumptions about these processes. Those assumptions are calibrated against observations of galaxies in the nearby universe. The question is whether the same assumptions hold in the very different conditions of the early universe. Webb's findings suggest that at least some of the assumptions need adjustment. The simulations typically predict fewer bright galaxies at high redshifts than Webb actually observes. This could mean that star formation was more efficient in early galaxies, converting gas to stars at higher rates than in later cosmic epochs. Or it could mean that the feedback processes that normally regulate star formation were less effective in the early universe. Or it could mean something more exotic, like a different form of dark matter or a time-varying dark energy that changed the growth rate of cosmic structures. Most astronomers currently favor astrophysical explanations over cosmological ones. The basic framework of lambda CDM seems solid, supported by multiple independent lines of evidence. It is more likely that the galaxy formation models need tweaking than that the fundamental cosmological model is wrong. But the door is not completely closed on more dramatic revisions. If observations continue to pile up that challenge lambda CDM predictions, Scientists will have to take those challenges seriously. That is how science progresses. Models are confronted with data, and when they fail, they are revised or replaced. One intriguing possibility involves the properties of dark matter itself. The standard model assumes that dark matter is cold, meaning its particles move. Slowly compared to the speed of light, cold dark matter clumps together readily under gravity, forming the halos in which galaxies grow. But what if dark matter has some properties that affect structure formation in subtle ways? Some theorists have explored warm dark matter, where particles move faster and resist clumping at small scales. Others have considered dark matter that interacts with itself or with normal matter in ways not included in the standard model. Webb observations of early structure formation provide new constraints on these alternative dark matter scenarios. Another area of active investigation involves the seeds of supermassive black holes. As mentioned earlier, Webb has found active black holes in very early galaxies, raising questions about how such massive objects formed so quickly. The standard picture involves black holes growing from stellar mass seeds left behind when massive stars die. But this process takes time, and the early black holes detected by Webb challenge the timelines. Alternative scenarios include direct collapse black holes, which form when massive gas clouds collapse without fragmenting into stars, and primordial black holes, which might have formed in the extreme conditions of the very early universe before even the first stars existed. Webb observations are helping to constrain which of these formation channels dominated. The connection between black holes and their host galaxies remains one of the most fascinating puzzles in astrophysics. In the nearby universe, there is a tight correlation between the mass of a galaxy's central black hole and the properties of the galaxy itself, like the velocity at which stars orbit in the galactic bulge. This correlation suggests that black holes and galaxies grow together, linked by feedback, processes that regulate their mutual evolution. But how far back does this correlation extend? Webb is finding that even in the earliest galaxies, black holes are already substantial relative to their host galaxies. Some observations suggest that the black holes might even be overly massive compared to the galaxy stellar mass, at least by the standards of the nearby universe. This could indicate that black holes grew first and galaxies caught up later, or that the feedback processes worked differently at early times. Understanding these relationships requires combining observations of both the light from stars and the light from accreting black holes. Webb's instruments allow astronomers to do both. The near-infrared camera captures the starlight, revealing the stellar populations of the galaxies. The spectrographs measure emission lines that trace gas dynamics and chemical abundances. The mid-infrared instrument is particularly sensitive to heated dust near black holes. By combining all these data streams, scientists can build comprehensive pictures of early galaxies as integrated systems, where stars, gas, dust, and black holes all interact. The technical capabilities of Webb continue to impress scientists as they learn to use the telescope more effectively. Early observations required conservative approaches because the instrument behaviors were not yet fully characterized. But as calibration has improved and operators have gained experience, they have been able to push the telescope closer to its theoretical limits. Observations that seemed impossibly faint at first glance are now routinely achieved. Spectroscopy of individual objects at redshifts above 10, which would have been science fiction a decade ago, is now standard practice. The telescope is performing even better than its designers dared hope. The Webb mission is managed by NASA in partnership with the European Space Agency and the Canadian Space Agency. ESA provided the Ariane 5 rocket that launched the telescope and contributed to 2 of the 4 science instruments. The Canadian Space Agency provided another instrument and the fine guidance sensor that keeps the telescope pointed precisely. Scientists from all 3 agencies and from institutions around the world participate in the science programs. The discoveries belong to the global astronomical community. This international cooperation is typical of modern space science. The challenges are too great and the costs too high for any single nation to tackle alone. By pooling resources and expertise, the space agencies achieve more together than they could separately. The same spirit of cooperation that built Webb is also advancing plans for future missions. The next generation of space telescopes, observatories even, more powerful than Webb, will require similar international partnerships. Astronomers are already dreaming about telescopes that could directly image Earth like planets around nearby stars, or detect primordial gravitational waves from the very first moments after the Big Bang. But for now, Webb remains the crown jewel of observational astronomy. Every week brings new results. Every month brings new record-breaking discoveries. The ancient galaxy at redshift 14.32 is just one landmark on a journey of exploration that has only begun. The telescope will continue operating for years, perhaps decades. Each year will bring deeper surveys, more refined measurements, and better understanding of the early universe. What will we learn next? That is the exciting part. Science is fundamentally about exploring the unknown, venturing into territory where the answers are not written in any textbook. Webb is humanity's probe into that unknown, our envoy to the distant reaches of space and time. The signals it sends back are messages from the past encoded in photons that have been traveling for billions of years. Decoding those messages is the work of a generation of astronomers who are lucky enough to live in an era when such observations are possible. The story of the ancient galaxy at redshift 14.32 is ultimately a story about human curiosity and ingenuity. We built an incredible machine and launched it 1,000,000 miles from home. We pointed it at a dark patch of sky and waited patiently while photons that left their source over 13 billion years ago finally arrived at our gold-plated mirror. We processed the data, analyzed the spectra, and learned something genuinely new about the universe we inhabit. That is an achievement worth celebrating. And it is a reminder that the universe is stranger, more surprising, and more wonderful than we expected. Our models did not predict galaxies this bright this early. Our theories did not anticipate this much chemical complexity so soon after the Big Bang. Reality exceeded our imagination. That happens a lot in science. The universe has a way of humbling our assumptions and rewarding our curiosity. Every time we build a better telescope, we find something unexpected. Every time we push our observations to new depths, we discover surprises. The James Webb Space Telescope has changed how we see the cosmos. It has rewritten the textbooks on early galaxy formation. It has challenged our models and forced us to think harder about how the universe works. And it has done all this in just the first few years of a mission that could last 20 years or more. Imagine what we will know by the time Webb finally stops returning data. Imagine what new mysteries will have been solved and what new questions will have emerged. That is the promise of exploration. Not just answers, but better questions. Not just discoveries, but deeper mysteries. The more we learn about the universe, the more we realize how much we still have to learn. That is not frustrating, that is exhilarating. It means the adventure continues. It means there is always more to discover, always another horizon to chase, always another ancient galaxy waiting to be found in the darkness between the stars. There really is no going back from this stunning revelation. The early universe is brighter, stranger, and more chemically and structurally complex than anyone predicted before Webb began its observations. Galaxies formed faster than our theoretical models expected. Black holes grew larger than our theories anticipated would be possible in such short cosmic timescales. Heavy elements appeared earlier than our simulations ever suggested was feasible. The story of cosmic evolution is being rewritten in real time, with new chapters and new surprises added every time Webb looks deeper into the primordial void. And somewhere out there in the cosmic darkness, light from even more ancient and distant objects is still traveling toward us on its epic journey across the universe. Photons that left their sources when the universe was even younger than when the earliest currently detected galaxies existed, before even the first stars ignited in the primordial darkness of the cosmic dark ages. Those photons carry encoded information about a universe we have never directly observed, an epoch we can barely imagine with our current scientific understanding. Someday, the James Webb Space Telescope, or its even more powerful successors, will catch those ancient photons too, decode their messages, and reveal new secrets from the dawn of cosmic time, and the magnificent story of discovery will continue unfolding. If you found this incredible journey through the vast depths of space and the immense reaches of cosmic time fascinating and thought-provoking, do not forget to hit that like button and show your appreciation. Subscribe to the channel if you want more compelling content like this, exploring the profound mysteries of the cosmos and the groundbreaking scientific discoveries that reveal them to us. We would absolutely love to hear your thoughts about this remarkable discovery and what it means for our evolving understanding of the universe and our place within it. Leave a comment below with your questions, your ideas, your theories, or just your emotional reactions to what the Webb telescope has found in the depths of space. Thanks so much for watching, and we will catch you in the next one. Word count: 17,404.